hard to believe that Alan and I have known each other for something like 35 years now, and I'm really excited about chatting with you and talking to you. Let me make sure I can share my screen and that you guys can see it. Can you all see that?
Yeah.
Okay. All right. So I'm going to talk to you today about the quest for other Earths. And so I just want to start with the fundamental question that we really are trying to address is are we alone? This has been a fundamental question that we have asked ourselves for literally thousands of years. And what this has translated to is the three very fundamental questions. Are there other planets in the universe? Is there another Earth out there? And is there life out there? And somewhat apropos to this is there intelligent life out there? And what's an amazing thing is that we are finally in a place in our culture and our community and our society that we can actually answer these questions. These three questions, which have been asked for thousands of years, we're finally at a place where we're actually beginning to address these questions and getting real answers to these questions. So this has been our vision of what planetary systems should look like for an extraordinarily long time. Now, not all of these planets were known for thousands of years. Uranus and Neptune and Pluto, of course, were discovered in 1700s, 1800s, and the 1900s. But in general, we've known about the solar system that it looks like this for the modern age and for modern astronomy. And when we went to go looking for other planets around other stars, this is the kind of solar system that we had expected to see. We had expected to see small rocky planets close to the star, big giant gas giants separated sort of in the middle of the solar systems, and then these ice giants further out. And the very first thing that happened was that we discovered a planet approximately 30 years ago. This planet was orbiting the star 51 Pegasi, and this particular discovery changed our entire view of the universe, because we did discover a Jupiter-sized planet, except that planet was in a 4-day orbit, as compared to, say, Mercury in our own solar system, which is an 88-day orbit. So not only was 51 Pegasi b about twice the size of Jupiter, but it was about half as massive as Jupiter. So it's this big giant puffball in a 4-day orbit around a star that's sort of like the sun. And this completely turned our understanding of exoplanet systems on its head, because our very first system looked absolutely nothing like what our solar system, what we expected systems look like based upon our solar system. And so we kept looking and we kept looking, and within about 10 years, we had found an additional 200 planets. So this is a graph of the mass of the planets that we had discovered by 2006 as a function of the orbital period in days. And so you can see that most of these planets are all about the mass of Jupiter. There are a few that we discovered by 2006 that were somewhere around the mass of Neptune. And a large number of them were all at orbital periods of a few days out to about 100 days. And we had started to discover planets that were out at orbital periods of like 1,000 days or a few thousand days, which starts to get near where the orbit of Jupiter itself would be. But you can see that all of the planets that we were searching for were quite massive that we had found so far. They were Jupiters and Neptunes, and there were no planets that we had discovered that were out around the mass of Earth. And so while we were discovering planets, we had not yet been able to discover Earth-sized planets. And so the European Space Agency and NASA took on two very specific projects to try to search for planets around other stars from space. The first mission by ESA and the French was called Corot, and it was launched in 2006. And then in 2009, NASA launched its Kepler mission. And both of these missions particularly used the transit technique to try to discover planets. So the way this technique works is that as the planets orbit the stars, if things are aligned in just the right way, the planet can pass in front of the star from our line of sight. And as it does that, it blocks some of the light from the star, and the apparent brightness of the star drops as the planet is in the front, and then the brightness of the star returns back to its nominal level as the planet gets out of the way. And this dip that we see in the light tells us that there's an orbiting body in front of the star that is blocking the light and therefore is most likely a planet. And this dip tells us about the size of the object. In fact, it's our most accurate way of determining the radius or the diameter of these objects as they pass in front of the star. And so the depths of these dips are about a 1% dip if Jupiter passes in front of the sun, and it's about a 0.01% dip if it's Earth passing in front of the sun. So this is a relatively easy detection to make. You can typically do it from the ground. In fact, the first transiting planets were detected from the ground before Corot or Kepler were ever launched. This is a much more challenging observation to make if it's an Earth-sized planet, because now we're talking about parts per million measurements in terms of being able to determine that a transit of an Earth-sized planet has occurred. The scatter in this light curve, as we measure the light of the star, is the same level of scatter that's in this light curve for the Jupiter-sized planet. So the precision required to get to this depth is much less than the precision that you need to get to this depth. And this is why we had to go into space. And to put this in the context of how small a dip in the light this is equivalent to trying to measure the brightness of a headlight of a car as a fly is walking across the front of the headlight. So it's an incredibly difficult measurement to make, which is why we put these spacecraft into orbit. So what did we find? Well, let's start with Corot. So Corot discovered about 40 planets, and they were mostly these very large Jupiter-sized planets in very short orbital periods. And there was a scattering of planets that it found that were about Neptune size. But most intriguingly, Corot found this very small inner planet called Corot 7. And what was interesting about Corot 7 was that this was the first time that we had identified a planet which we could safely say that we knew had to be rocky. We had the size of the planet from the transit, and we had gotten the mass of the planet from the radial velocity, which I didn't talk in detail about how we do radial velocities, but we got the mass of the planet from the radial velocity measurements of the star as the planet orbited around, and we were able to determine that the size of the planet is only about 60% bigger than that of the Earth, but it's about twice as dense as the Earth. But it's in like a 3-day orbital period. It's an incredibly short orbital period in comparison to the Earth. And so almost certainly that this world is some kind of very hot lava world, and its ability to hold on to water, let alone life, is probably next to impossible. But this planet and this spacecraft's detection of that was the taste that we needed in order to move on to the next stage, which was what we've discovered with Kepler. And Kepler absolutely enabled a revolution in our understanding of exoplanets. So this is about what the discoveries looked like before Kepler. We had a large number of planets that we had discovered, both from the ground and with Corel in space, that were mostly Jupiter-sized and Neptune-sized. And there was starting to be a scattering of planets that were down near the mass of the Earth. But we really hadn't really gotten to Earth mass-like planets quite yet. And by the time we got to the end of Kepler, this is what the plot looked like. It was just dominated by planets that were near the size of the Earth and planets that were near that were in between the size of Earth and Neptune. But as you can see, we actually didn't find any planets that were far enough out in orbital period and the size of the Earth to find exactly Earth-like twin quite yet. But this body of planets that Kepler discovered enabled us to begin to explore the diversity of exoplanet systems that have been discovered. And mostly what we have found is that there's a whole host of planets and planetary systems that are not like our own solar system. And in particular, one thing that we discovered that we didn't really understand existed as much as they do after Kepler is the existence of super-Earths. So these planets, which are in between the size of Earth and Neptune, these kinds of planets don't exist in our own solar system, but they actually make up the majority of the planets that Kepler discovered. Most of the planets that Kepler discovered were either 1 to 2 times the size of the Earth or 2 to 4 times the size of the Earth. And so this grouping of planets, which we call super-Earths and many Neptunes, turns out that they are one of the most common types of planets that the universe produces, and yet they don't exist in our own solar system. And one of the questions that Kepler introduced into our understanding of how our own solar system was formed is, why do the super-Earths and the mini-Neptunes not exist in our own solar system? Where are they? They're almost in all of the other systems that Kepler discovered. Why do they not exist in our own solar system? And to this day, that's one of the questions that we're still trying to address. But Kepler did find some very intriguing systems. It found planets that were smaller than Mercury. So Kepler 37b is actually about the size of the Moon. And in particular, if Kepler 37b existed in our own solar system, we might not have classified it as a planet. We might have classified it as a dwarf planet. So for all the people who love Pluto, there is still yet hope that Pluto might get reclassified as a planet as we begin to bring the exoplanet world and the solar system worlds together. Kepler also found entire solar systems that were about the size of Jupiter's system. So this is Kepler 42. It had 3 planets. So the star itself is actually much, much smaller than the sun. It's some kind of, I forgot exactly what it is, but it's some kind of mid-end dwarf. So it's only about twice the size of Jupiter itself. And the entire system is actually at the same scale, is about the size of the Jovian system. So entire solar systems that would fit inside our own solar system were being discovered by Kepler. The other thing that Kepler discovered, we sort of knew that these existed, but we didn't understand at what scale these existed. And these are systems that have multiple planets. So we know, of course, that our solar system has 8 planets, 9 if you include Pluto. excuse me, and we had started to discover a few multi-planet systems, though most of them were only systems with 2 or 3 planets. This system that was shown here is Kepler 11, it's Kepler 11, or Kepler 9, sorry, it's Kepler 9, and it has 6 planets in an incredibly tight, compact system. So all 6 planets in this system could fit inside the orbit of Venus, and the inner 5 planets actually could all fit inside the orbit of Mercury. And the size of the star for Kepler 9 is about the same size as the sun. So it's not just a function of the size of the star, because the stars are about the size of the sun, but there's something very different about how Kepler 11 was formed versus how our solar system was formed. Sorry, I said Kepler 9, it clearly is Kepler 11, my apologies. But this was just one system. And it turns out that Kepler discovered thousands of multi-planet systems. And this is a plot of all of those systems to the same scale. You can see the dotted lines. This is our solar system. And then each of these individual points, these are all of the individual multi-planet systems that Kepler discovered. And you can see that they have a range of sizes and orbital periods, and they're compact. Some are bigger, some have many planets, some only have 2 or 3 planets. But one of the things that Kepler pointed out to us was the breadth of diversity of planetary systems that the universe is capable of producing. But Kepler's prime mission was to understand how common small Earth-like planets might be. And the planet that we discovered that was most like the Earth around a sun-like star was Kepler 452b. It's about twice the size of the Earth, and it orbits a sun-like star in something like a 350-day orbit. So it's probably very similar to the size or to the environment of Earth. But because its size is so much bigger, its mass is actually quite a bit more than that of the Earth. And in fact, it likely, you and I, if we were to fly there, could not actually easily stand up because the gravity would be too strong for us to be able to stand up. So this is not quite Earth-like. And so we're still at that quest of trying to understand how common and what they're like, what Earth-like planets are actually like. But then it was also filled with other surprises. So for example, it discovered Kepler 16. Kepler 16 is a planet that's actually orbiting 2 stars. The 2 stars actually orbit each other, and then the planet orbits around both of the stars together. This was nothing like we had ever seen before, and in fact, there have been papers suggesting that this kind of configuration was not actually possible, that the gravitational interaction of the 2 stars would prevent any planets from ever forming in that environment. And yet, Kepler discovered not only one, but dozens of these kinds of systems, showing that indeed circumbinary planets not only exist, but they're actually relatively common. So it turns out that there was a philosopher in the 1970s who actually predicted this, unlike the scientific papers. And he was way ahead of his time in his ability to predict what we should have seen with Kepler. And that was George Lucas. It turns out, actually, that Ptolemine, orbiting these 2 stars, is about the right scale for Kepler 16. Those 2 stars on the horizon, as they begin to set, are about the right separation and actually the right scale, as if George Lucas had known that we were going to discover Kepler 16. Our only hope is that George Lucas is not completely correct and that we're not on our way to this. I really hope there's laughter in the room. It's kind of hard to tell. It had a finite amount of fuel for pointing. And so that fuel ran out, and we said goodnight to Kepler in 2018. And in the end, Kepler observed 500,000 stars and discovered about 2,700 planets that were fully confirmed. There's another few thousand planets that Kepler discovered that are still that still need to be confirmed as true exoplanets. And in the end, it continued. You know, when this graphic was made, 3,000 papers had been written based on the Kepler data, and that's still that legacy of Kepler is still happening, and papers based on Kepler data are still ongoing. It is one of the richest exoplanet data sets that we have available to us. But one of the problems with Kepler is that the stars that it observed and discovered planets around were actually relatively faint, making follow-up and characterization really difficult. So the typical Kepler star had a brightness of something like 13th to 16th magnitude. And while that's not super faint for, you know, a relatively small, even for a relatively small telescope to be able to observe it, it is actually relatively faint if you're going to do deep, very detailed, high precision observations, even with the largest professional telescopes in the world. So to try to correct this, we wanted to go and find planets around brighter stars, nearby stars, in order to do a better characterization of those planets that we discover. In order to do that, because there are fewer brighter stars in the night sky than there are fainter stars in the night sky, you actually need to survey the entire sky, not just a patch of sky, the way that Kepler did. And that mission was designed during the Kepler years and actually launched just a few months before Kepler came to an end. And that's the Transiting Exoplanet Survey Satellite, or TESS. And this is NASA's current ongoing exoplanet finding mission. And the way that TESS works, it's like Corona. It is looking for transiting exoplanets, but it's doing it over the entire sky. So it has these 4 cameras, and it points at a particular spot in the sky for about a month. It then rotates, it points at that part of the sky for a month, rotates, points at that part of the sky for the month, and then it maps out the entire hemisphere. It flips over, and then it maps out the other half of the sky. And it continues to do this. So its initial mission was 2 years. So the first year was one half of the sky. The second year was the second half of the sky. And it is now operating into its 3rd extended mission, and it has mapped out the sky 4 times at this point. And so TESS has extended our understanding of exoplanets by helping us to find brighter stars, which are hosting exoplanets, which we can now characterize. And we're now up to, as of just yesterday, about just under 6,000 known exoplanets. So stop and think about that for a moment. So the first exoplanet was discovered in 1995, which was 30 years ago. This is the 30th anniversary of 51 Peg. And in 30 years, we've gone from knowing about the 8 planets in our own solar system. Actually, at the time, it was 9 planets because Pluto was still a planet in 1995, to 1 planet outside of our solar system in 1995, to 6,000 planets around 4,000 stars in 2025. And the discoveries just keep on coming. And what this is starting to enable us to do is not just study individual planets and individual systems, but we can now start to see populations of planets. Patterns are beginning to show up. So for example, we have the hot Jupiters. These were the first kinds of planets that we discovered. This was 51 Peg. It was a hot Jupiter, a Jupiter-sized planet in a few-day orbit. The temperatures of these planets are a few thousand degrees. And it's pretty clear that these kinds of planets actually could not form where we see them today. They had to form much further out in their systems, migrate in, and then stop migrating inward before they crash into their stars and park themselves right at these few day orbits. So this has implications for if there's a hot Jupiter in the system, it's not clear, one, what caused the migration, and two, if there were other planets in that system when those Jupiters formed, what happened to them as the Jupiters migrated through? Did they get scattered out of the system and they're lost forever? Did they get scattered into weird orbits that we just can't find them? Are there a bunch of small planets which are just freely floating through the universe with no host stars? We also found a plethora of giant stars, much like what we had expected, right? Jupiter and Saturn are at orbital periods of 12 or 10 and 30 years or something on that order for Jupiter and Saturn. And so we're beginning to find a group of planets which are out there, but also notice that many of the giant planets that we're finding are actually much more massive than Jupiter. They're 2 or 3 or 4 times the mass of Jupiter, and not just Jupiter sized. We also found a bunch of really hot rocks. So this is like Corot 7. So these are super hot, very close to their stars. They are almost certainly rocky because they're small and the masses that we have to them indicate that the density must be some kind of rock. But did they form right there, or did they migrate in? How did they get there? Right, so they could not. These systems also almost certainly could not have formed right where they are because the volatiles would have evaporated off, and these systems would be much more dense, like iron would be. But they're not that dense. They have densities that are much more akin to the Earth or Earth-like, and therefore they also were likely further out and then migrated in. We also have found a plethora of ocean worlds and ice giants. So these are things that we think that are akin to Neptune and Uranus. The ones that are closer in, maybe they have liquid water, maybe they are slightly they have to be slightly warmer than the Neptunes and Uranuses that we think about. And the systems that are out here, they might be more Neptune-like and Uranus-like. But Uranus and Neptune are actually very different from each other. They have very different densities. They have very different structures in their atmospheres. And so it's quite possible that there's a huge variety of demographics in this grouping just alone because of the kinds of planets that they contain. And then finally, the rocky worlds, right? So these are the planets which we really think are much more Earth-like in terms of their structure. But the real question is, are any of them actually Earth-like, or are they just Earth mass and Earth-sized? And so what we'd really like to be able to do is try to find a way to get detailed characterization of these individual planets, directly image them, for example. And so we've been working for a long time to try to directly image planets. And this is, of course, what we hope to do, but the reality is much more bleak. The problem is that the stars are literally 1 billion to 10 billion times brighter than the planets we're trying to find. And so the planets are hidden in the glare of the star. And this is a graphic, obviously, but I want to pause for a moment here and let you look at this graphic. So somewhere in this graphic, there is a firefly hidden in the glare of the lighthouse. And I can't see any of you, but I'm going to pause for 30 seconds and see if you can pick out the firefly. I'm not going to pause for 30 seconds because that's forever in a talk, but I'll pause for a moment here. And so if we could turn off the lights, we can then go and find the planet that we're trying to look for. And this is exactly the problem that we were trying to find, is to pull those planets out of the glare of the star. And so we do that by building what we call a coronagraph. So we image the star, and then we put a blocker in front of the star. We literally block out the light from the star. It's much like what you would see during a total eclipse of the sun, when the moon passes in front of the sun, then you can then see the corona of the sun, which is normally hidden in the glare. And that's in fact where the term coronagraph comes from, is that it was originally designed to study the corona of the sun by blocking out the light from the sun. And so we started to build these coronagraphs and put them on telescopes starting on the ground, because we always start on the ground where it's actually easier to do stuff than it is in space. And what's amazing is that we're actually beginning to discover full-blown solar systems. And we're watching those solar systems evolve in time as we observe them again and again and again. So the system on the right has 4 planets, and this montage of imaging was put together over the span of about 10 years. And you can actually see the planets orbiting the star. And the system on the right, this is Beta Pictoris in the southern hemisphere. The planet was discovered about 10 years ago, and we realized that the planet was moving in a direction such that it almost crossed in front of the dead center of the star. So this, in the end, this planet did not actually transit its star, but it became very close. So one of the limitations of these ground-based systems is that they're mostly relegated to imaging very, very young and very large planets. And that's because while we block out most of the starlight, we still are we're still limited by the technology, and in particular by the Earth's atmosphere jumbling up the observations. That while we can get down to, we can reduce the starlight by a factor of a million or a few million, it's still really hard to drop that light down by a factor of 1 billion in order to get to see an Earth-like planet. That is why going to space is so powerful, is because if you remove the Earth's atmosphere, then the observations become much more stable, much more capable of getting to fainter and fainter brightnesses of the planets. And the premier telescope in space at the moment is the James Webb Space Telescope, which has been in space now for about 4 years, and it's starting to really revolutionize our understanding of exoplanets by enabling us to characterize individual planets in a way that we couldn't do from the ground. So one of the things that JWST does is it enables us to directly image planets, just like I was talking about from space. So these are 4 early examples where you can see that the light from the star has been blocked out in each of these cases, and the planets just show up as enormously bright, easily detectable. And what's powerful about the James Webb Space Telescope is it's enabling us to get down to planets which are closer to the size of Neptunes and those mini Neptunes and super Earths. And it's also enabling us to not only get images like this, but also to get spectroscopy of the planets at a level of precision and at a level of detail like we have never seen before. So this is an early release of one of the early spectra that James Webb took. And one of the things that immediately stood out was the fact that this particular planet has methane and carbon dioxide and hints of a molecule called dimethyl sulfide, which I'll talk about more in a moment. And while this planet was a Neptune-sized planet and was never expected to have any kind of signatures of biology on the planet, the fact that we can see things like methane and carbon dioxide very easily in these spectra, beginning to tell us that we can do that kind of analysis on more and more planets with this 6-meter telescope in space. And in fact, one of the early campaigns with James Webb was to go after the TRAPPIST-1 system, which has 7 Earth-sized planets, 3 of which are actually in the habitable zone of the system. So TRAPPIST-1 itself is a very ultra-cool star. It's about 1/10 of the mass of the sun, and the fact that it has so many Earth-sized planets suggests that it's actually relatively easy to make Earth-sized planets in the habitable zones of small stars in a way that may not be possible around bigger stars like the sun, which produce things like Jupiters and Saturns, which actually might prevent Earths and Venuses from forming at such the same rate and frequency. And in fact, we think that the majority of Earth-sized planets in the universe are actually around these very cool M stars. So one of the things that we're interested in is if any of these systems have atmospheres around them that might indicate that they are capable of supporting life. And while all of these are currently being observed in detail by James Webb and those studies are ongoing, the first planet in the system, TRAPPIST-1b, was actually observed very early on in the JWST mission. And what we had expected to see is that if TRAPPIST-1b had an atmosphere, that we should see data somewhere down here at these wavelengths. And this wavelength is somewhere around 15 microns. And we should have seen a flux that was down around here. And what we actually saw was data that was way up here. And so what that told us was that the planet TRAPPIST-1b actually has no atmosphere. And while we weren't surprised that TRAPPIST-1b didn't have an atmosphere because it's the planet that's closest in to TRAPPIST-1 itself and is therefore the hottest and therefore most likely to have evaporated its atmosphere, the fact that we're able to do the measurements at these precisions means that when the data start coming in on the other TRAPPIST systems, we'll be able to make more definitive estimates as to whether or not they have an atmosphere or they don't. Now, you may have heard in the last month or so in the news that JWST actually did find life on a planet called K2-18. So they measured the spectrum of this planet where they think they see dimethyl sulfide and dimethyl disulfide. And these are molecules which we think are produced by life, things like plankton in the oceans. Now, the problem with this particular observation, one, it's incredibly, this is an incredibly difficult set of measurements, and it's incredibly exciting to think that this might be real. But the amount of dimethyl sulfide that they need in the atmosphere in order to see this is about 1,000 times more than the dimethyl sulfide that we would see in our own Earth. And we know that there's plankton in our own oceans. And so exactly how you would get this kind of amount of dimethyl sulfide in the atmosphere isn't entirely clear. Maybe it's a planet with a massive amount of plankton in the oceans. It's hard to know. But another part that you guys should always keep in mind is that the difficulty in these measurements, and it turns out these measurements are also just as statistically equivalent to them being a flat line, and that the bumps that we see in the spectrum are actually just levels of noise. So is this just a flat line with a lot of noise on it? Or is it really a spectrum that we think has pieces on it? That's how science works. The next step is to get better and more detailed observations and try to not only understand this system by itself, but understand this system in the context of all the other planetary systems that we have discovered, or as many as possible. And so building towards finding Earth 2.0 really is a suite of observations that are being supported by NASA and our partners, particularly ESA in Europe, both in space and on the ground. So these missions include things that I've already talked about, like Kepler and TESS and COROT, but there's a whole suite of missions where we bring all of these data together. And I want to talk about two or three of the next upcoming missions, which will really help us try to understand the next stage of what kinds of planets are we finding and what do they look like and what do they might possibly hold. So NASA's next big mission is called the Roman Nancy Grace Roman spacecraft. And it's designed to fly the most sophisticated coronagraph ever built and to operate in space. And it's designed that it will find planets around other stars that are smaller than Neptune size. They'll get down to the super Earths. It probably won't quite get to the Earth-sized planets. It's not quite that powerful enough yet, but it's the next stage in helping us to discover and directly image planets which are much closer to the size of the Earth and in orbits like the Earth. And this is a key fundamental mission which will help advance the technology and advance the science in helping us how to do these observations. There's also another mission which is being launched by the Europeans, which NASA is a partner in. This is called Ariel, and it's designed to do spectroscopy of 1,000 exoplanets. And that means that we can then begin to understand the chemistry of all of those populations that I was talking about. So Ariel will observe planets which are hot Jupiters, and giant planets, and ocean worlds, and rocky worlds, and even lava worlds, and try to put together an understanding of how all of those, what the chemical composition is of those worlds. And by building a statistical census, we'll be able to much better understand not just one system or two systems or even our own system, but how all of the exoplanet systems come together as a whole. And where does our own solar system fall within that context? And that mission is likely to launch at the end of the decade. It's currently in its building phase. And as I mentioned, NASA is a partner in that. But this is all really leading to the inevitable mission that we really want to fly, which is called the Habitable Worlds Observatory. This mission is designed to directly image an Earth-like planet in an Earth-like orbit around a sun-like star. And it's going to use the technology that we've been talking about, these coronagraphs, to block out the inner part of the star, but at a level where we expect to be able to see a Venus and an Earth. The Jupiters and the Saturns will be duck soup. Those will be super easy to find. Venuses will be at the edge because they're a little bit too close to their stars. But the mission is being designed to find an Earth in a one-year orbit around a one solar mass star. But once we discover it, we're kind of left with, okay, now we need to take a spectrum. And what is that spectrum going to look like? And it turns out, and perhaps not surprisingly, that the Earth, if you were to take a spectrum of the Earth over the course of its lifetime, that it doesn't actually look the same today as it looked billions of years ago. because the content of the Earth's atmosphere has changed dramatically, partly because the Earth, a few billion years ago, started to develop life, and that released oxygen into the air. So early on, the Earth was dominated by methane and carbon dioxide, and now it's dominated by water and oxygen, and all the molecules that we think about are associated with life. And so when we go and actually get a spectrum of one of these Earths that Outer Worlds Observatory might discover, we're not just going to be left with does it have life, but we're going to need to understand where in the stage, how old is the star, how old is the planet? And so understanding the entire system as a whole is crucial to understanding what it is that we're about to observe. And so we don't just study the planets, we study the entire systems as a whole. We study the stars, we study the planet we're interested in, we study the other planets in those systems, and we put that in the context of all the other planetary systems that we've discovered. Plus, we have to put it into context of chemistry and biochemistry, and evolution, and all of the pieces that go into making what the Earth is today. And so as I come near the end of this talk, I just want to return back to the three original questions that I posed at the very beginning. And the first is, are there other planets in the universe? And I think one amazing thing to say is that we know this answer to be yes, as a resounding yes. And it's really incredible. I'm not sure who's in the audience and the ages of the distribution of people in the audience, but I can tell you that when Alan and I were in college, there were 8 planets known in our solar system, and that is it. And in the span of our adulthood, not even our entire lifetime, but just in the span of our adulthood, we would turn that answer into it as a yes. And every week, we discover more and more planets. Is there another Earth out there? The answer is almost certainly yes. It's really hard to imagine that we won't discover that. Certainly, we haven't actually discovered that at this moment, but we're getting closer and closer every year, every week, every month. And this is a strong push by the entire scientific community. And let's be honest, is of interest to a large fraction of the population outside the scientific community. This is a fundamental question about who we are and from where we come from. And so that leaves us with this final question: is there other life out there? And it's hard to think that the answer is no, but we just don't know the answer yet. Maybe the Earth is indeed special and unique, and while special, maybe it's also not unique. And only time will tell. And so I just want to leave with a final thought. Imagine what you will know tomorrow, because what you know today is either wrong or incomplete. And then finally, before I could not help myself, I really wanted to indicate that I went to the library when we were in college, and definitely cheesy mustaches in 1989 were all the rage. But there we go, proof that Alan was in the library at college, and then he did indeed graduate. Thank you. I hope you guys were able to enjoy the talk. And I'm sorry I could not be there in person.
All right, thank you. We've got a couple of minutes for any questions that you might want Dr. Ciardi to answer. Yes.
You thought about travel to a wormhole, in other words, speed things up.
Yes, whether or not there's any possibility of faster than light travel as far as being able to get to any of these exoplanets. I guess one of the first questions you would have to answer is what's the distance that we're talking about when we're looking at exoplanets? Are we 100 light years? Are we 1 million light years? Anything like that?
Yeah, so So the closest stars, so the closest star to us is Alpha Centaurus, and that's about, it's about 4 light years away. The majority of the systems discovered by tests are tens of light years to 100 light years away. And the majority of the systems discovered by Kepler are actually quite distant. They're many hundreds to thousand or a few thousand light years away. So to answer your question about faster than light travel, the way that we understand physics, the answer to that question is no. We don't understand, the way we currently understand physics, there's no way for us to go faster than the speed of light. Having said that, that doesn't mean that we understand physics in its entirety. And is there something that we don't understand that might enable us to be able to do that at a future time? That answer is always yes, there's a possibility. And so should you pack your bags today? Probably not. But could future generations begin to think this through? If we discover something new and different in how the universe is put together, I would never rule that out. Never underestimate the ability of nature to confuse and confound you.
Any other questions? All right, if not, thank you very much, Dr. Ciardi. Appreciate your time, and say hi to the family for me.
I'm sorry we couldn't do this in person. We'll have to figure that out.
Yeah, one of these days you're really going to have to come to Yellowstone so that we can party.
Well, you guys enjoyed it. It's very hard for me to see the audience. I hope it was enjoyable and informative and at a level that made it exciting for the group of you. Enjoy the night skies. I don't quite get them in Los Angeles the way you guys get them in Montana.
All right, thanks, Dave. See you
Take
later.
care, everybody.